You know, when we think about processing something as complex as head motion, our minds usually jump straight to the brain, right? But what if I told you that some really sophisticated signal processing happens way before any information even gets close to the brainstem? It's happening right out in the periphery, thanks to the incredible diversity of our vestibular hair cells. Today, we're going to explore how two different types of these cells act as powerful temporal filters, literally shaping our perception of movement from the very first moment.
Welcome to this explainer from Australian Dizziness Clinics. In this session, we're going to get right down to the nitty-gritty and connect the dots between the biophysics of individual ion channels and this crucial function of temporal filtering in our vestibular system. So, let's jump right in.
Okay, first things first, let's get one crucial concept straight. Vestibular hair cells are not just passive mail carriers simply relaying a signal. No, they are active computational units. They fundamentally shape and filter information about head motion. They're like editors, deciding which features are important enough to get sent onto the brain for the next level of processing.
And here they are, the two main players in our story today. On the left, you've got the flask-shaped type I hair cell, which is almost completely hugged by this unique nerve ending called a calyx. And on the right is the more classic cylindrical type 2 hair cell connecting to several smaller bouton endings. Now, they obviously look different, but as we're about to find out, when it comes to their electrical functions, they are on completely different planets.
Let's start with the type 2 cell. You can think of this one as the OG, the ancestral hair cell. It's the foundational design that's been optimized over evolutionary time for one primary purpose: stability.
So what's its secret? Well, the key to the type 2 cell stability is its specific toolkit of ion channels. It has a whole suite of potassium conductances that essentially act as governors on the system. Their whole job is to prevent the cell from depolarizing too much or too erratically. This allows it to produce a really steady, graded signal that faithfully represents a sustained stimulus.
And the result of having these specific ion channels is an incredibly high input resistance. We're talking about 1 gigaohm. That's huge. It basically means the cell membrane is extremely well insulated, almost like a perfect wire. Very little electrical current leaks out, which in turn makes the cell highly sensitive to even the smallest currents generated by head motion.
Now, this high resistance directly leads to what we call a long membrane time constant, or tau. And the best way to think about this is like the suspension on a luxury car. It's a shock absorber. It doesn't jolt with every tiny little bump. Instead, it integrates or averages the incoming signal over time, effectively smoothing out the ride.
So the bottom line is, the type 2 cell acts as a signal integrator. Its biophysical properties make it perfectly designed to encode tonic or sustained information. Things like holding your head in a tilted position or moving at a constant speed. It gives the brain a nice, stable, smoothed-out report of our orientation in space.
Okay, so that's our stable integrator. Now let's completely flip the script and look at the type 1 cell. If the type 2 is the reliable family sedan, the type 1 is a souped-up race car. It's a remarkable evolutionary specialization that's been engineered for one thing above all else: speed.
And the secret to all that speed comes down to one single game-changing feature: a massive potassium conductance known as IKL. This channel is a total outlier. It activates at very negative membrane potentials. And when it does, it basically throws the entire electrical rulebook we just established for the type 2 cell right out the window.
You see, this IKL channel is always a little bit ajar, even when the cell is at rest. This creates a constant leak of potassium ions flowing out of the cell, and this leak absolutely tanks the cell's input resistance, dropping it all the way down to around 10 megaohms.
Let's just pause on that for a second. The type 2 cell was at about 1,000 megaohms. The type 1 cell is at 10. That is a 100-fold difference. It's an enormous biophysical shift. This makes the type 1 cell electrically leaky. And believe it or not, that leakiness is its superpower.
This extremely low resistance leads to a very, very short membrane time constant. So, going back to our car analogy, this is like a race car with incredibly stiff suspension. There is absolutely no smoothing. The cell's voltage can change almost instantaneously, tracking incoming signals with extreme fidelity and almost zero electrical blur.
And that right there is the core purpose of the type I cell. It's a signal tracker. It's built to encode the phasic stuff, the fast, transient, high-frequency head movements we make all day long, like when you quickly turn to look at something.
So what do we got? We have two totally different cell types with vastly different electrical properties living side by side.
This isn't just some redundancy. It's a really sophisticated filtering strategy. Let's put it all together.
This table just lays it all out perfectly. You have the type 2 cell with its high resistance and long time constant, acting as a slow integrator for tonic signals. And then, in total contrast, you have the type 1 cell, which uses that special IKL channel to get low resistance and a short time constant, making it a fast tracker for phasic signals. It's really elegant. 2 different cells, 2 different filters, creating 2 parallel streams of information.
So why does all this matter clinically? Well, here is the crucial connection. That incredible speed and temporal precision of the type 1 cell is the biophysical foundation of our high-frequency vestibulo-ocular reflex. It is literally what allows us to maintain stable vision during rapid head movements, a cornerstone of vestibular function. Okay, let's boil all of this down into the 3 key clinical takeaways that really summarize why this cellular diversity is so important. First, type I cells are built for speed. They provide that high-fidelity signal that's absolutely essential for fast reflexes like the VOR. Second, type I cells are built for stability. They provide the smooth, integrated signal we need for our sense of orientation. And third, and this is the big one, this diversity is the whole strategy. It's a deliberate and elegant filtering system designed to make sure the full spectrum of head motion, from the fastest flick of the head to the slowest tilt, is captured and sent to the brain.
So, we've seen how these 2 cells work as temporal filters. But the story of the type I cell gets even wilder. I hope you'll join me in video 9, the calyx paradox, where we'll discover how that unique calyx synapse actually runs 2 transmission channels at the same time, including a bizarre physics-based mechanism that is faster than any conventional chemical synapse we know of.
Thank you so much for joining me for this session. To explore more topics on dizziness, vertigo, and imbalance, and to get some great resources for both clinicians and patients, please visit us at australiandizzinessclinics.com. And of course, we'd love it if you'd subscribe and leave a rating.